Okay, I think we're ready to start. So welcome to the JINA online seminar, and our speaker today is Stephan Stetina from the INT in Seattle, and he will tell us about the photon and dense nuclear matter.
Thank you. I hope everybody can hear me, and thanks Ingo for a nice introduction. It feels a little weird to be the one who gets actually announced in the seminar. So today I'd like to use the opportunity to show you some of the work I've done recently together with Sanjay Reddy and NRAPR, who is now a postdoc at the University of Guelph. And the core idea of this project is to understand as accurately as possible how the photon spectrum looks like in dense nuclear matter. So let me tell a little bit of why we are interested into this. So I'll say some words about the relevance of all of this to the phenomenology of complex stars. Then I'll say some technical remarks, not too many, because I know this audience is very mixed. So we have a lot of astrophysicists in there who are probably not that much interested in this, but I should say at least a little bit to show you how we're actually obtaining our results. And then I want to discuss specific results, which are very interesting, in particular, single and multi-component plasmas and the impact of induced interactions. So why are we interested in this? So if we look at the photon spectrum in the core of a neutron star, it is subject to a lot of physical effects. So you will find collective excitations, you will find screening, most notably lambda damping. And all of this is based on the exchange of electromagnetic interactions and strong interactions. So if you want to connect that with something that's observable in a neutron star, then transport theory is an obvious link between the microscopic physics and the macroscopic ones. So in particular, there's a damping and relaxation of hydrodynamic modes, which is strongly influenced by this. One particular example of this is the damping of R modes. And then there is the neutron star spin evolution. And then another thing that's interesting in this context, and I put it in brackets here because it's actually not really related to transport theory, but nevertheless interesting, is the production of neutrinos in dense matter. So neutrinos can be produced by the decay of plasmons. So for that, the collective mode spectrum is also very relevant. So here's some of the pioneering work that has been done so far in the calculation of transfer properties in neutron star cores. I should point out at this point that we're really talking about well-established aged neutron stars. So we're not talking about the first seconds after supernova explosion where thermal effects can be important. So we're looking at cold and dense nuclear matter. So there has been done some work by Flau and Ito back in 1976, and more recent works by Sternen and Yakovlev, who calculated the transport coefficients in some more detail. And one contribution that's very important to transport coefficients is that of electrons, simply because electrons are very light. In the relativistic limit, you could even consider them massless. They degenerate and they're weakly interacting. So for those reasons, they're certainly a main contributor to any transport coefficient or transport effect. So usually what one does in the calculation of transport coefficients, one assumes the collision energy and momentum transfer to be small, which is certainly a reasonable approximation. And then looking at screening, what is usually done is people work in the weak screening approximation. So the longitudinal spectrum of the propagator is screened by the biomass. The transfer spectrum, in principle, if you only consider static screening, is not screened at all. So unless you're in a superconductor where you have a Meissner mass. But in normal phase, there would be no screening, no static screening to the transfer propagator. As a matter of fact, it was figured out by Heiselberg, Bay, and Pathak et al. That the exchange of transverse photons is actually the dominant mechanism for electrons to scatter. So when you are in a dense plasma, electrons are not scattering by the exchange of a standard photon. The photon gets a lot of medium correction, so electrons are actually scattering by the exchange of plasmons. And it was figured out that for relativistic transport coefficients or for relativistic interactions, it is actually the transfer photon that dominates. So that's a very strong argument why people should be interested in dynamic screening effects, because that's basically the only kind of screening we have for those interactions. So what we really want to do is we want to obtain a photon propagator in a dense plasma that's comprised of electrons, muons, protons, and neutrons in a region of small energies and momenta, but with the full dynamical screening that you can get to a certain approximation. So technically, what is it that we're doing? It really comes down to inverting the Dyson equation for the photon propagator. So d tilde is the full resummed propagator, d is the free propagator. So as I said, we're aiming to work in a fully relativistic setup, which is certainly appropriate for leptons in the core. One important aspect or technical detail that one has to mention is the gauge that you actually choose. The photon propagator per se is a gauge-dependent object. So there might be quantities that you can extract from it which are not gauge-dependent, such as the spectrum of low-energy excitations. But if you were to use that propagator later on, I have to tell you in which gauge it was actually calculated. So in this case, we're calculating the dressed photon propagator in Coulomb gauge, which has the very nice feature that it gives you right away the physical longitudinal and transverse spectrum without having to worry about contributions from ghosts. So people are usually calculating the response functions in the framework of linear response theory. So it's worth pointing out what these objects d and pi actually are when you look at it from the point of view of linear response. So if I apply an external current to the system, then the response function is the dress propagator. If I apply an electromagnetic field, then the response function is the photon polarization tensor. So actually from these two definitions, you can get back to this definition of the self-energy of the photon. But this is what they mean in linear response theory. So what does the RPA actually do? RPA is basically a fancy word for doing a one-loop resummation. So if I take my photon propagator and I resum insertions of electron loops, of single electron loops, and that's pretty much what the RPA is doing. So at that point, you could say, well, if I'm in a plasma, I should probably do the same thing for the fermions. So and you could basically write down a Dyson equation for the fermions as well. In cold and dense matter, the alpha F corrections to the fermion propagator are actually not that relevant. So we are really going to focus on the Dyson equation for the photon and treat the leptons as bare particles. Also the protons as far as electromagnetic interactions are concerned. Of course, strong interactions then modify the picture. So protons really are quasi-particles in the strongly interacting plasma. And then we're going to look at the imaginary part that arises from lambda damping in the region of small energies.
I know what alpha is. What's alpha F?
And alpha F is the fine structure constant. So.
F for fine structure.
So that's basically e squared over 4 pi. Well, thank you for pointing that out. So let's look at a single component plasma. So that's kind of an academic exercise because one could argue that, well, in a single component plasma at very high densities, the system is not charge neutral. And that's certainly true. Nevertheless, these are plots that lots of people have seen before. So it's kind of a natural starting point to start with a one component plasma. So you can take the real part of the polarization function and calculate the excitation spectrum that you get basically from solving these two equations. So if you are at very low momenta, you can actually extract analytic results. So you find one plasma mode, which has a plasma frequency of e squared over 3 pi squared kf cubed over mu, so that you can work out analytically. So that's actually a gapped mode. But you also find an ungapped sound mode in the spectrum, or sound-like mode, so a mode that goes to 0. And then you can do the same thing for the transverse mode. So in total, you find a spectrum of 3 modes, 2 longitudinal ones, and the plasma mode, and the transverse mode. And so on the left, you see the system for a single component plasma comprised of electrons, and on the right, you see it for protons. So in lots of literature, you find reported that in the case of very massive particles, like protons, the excitation spectrum becomes like gets a thumb-like shape. So you can see that it ends at some point very abruptly. That's reported in a lot of literature. In the next slide, I will say a little bit about why this is happening. In the case of electrons to the left, you can see that they basically asymptotically approach the dashed line. The dashed line is just the light cone. So for ultra-relativistic particles, the longitudinal modes asymptotically approach the light cone. And the dot dashed line, that's the line c times vf times q. So that's where you can calculate this constant c, and it's 0.08. It's something slightly below 1.
So this is a one component of the bottom where charge neutrality and both systems are assured by some background jelly that is not dynamical. So it's a jelly model or no?
You could think of it as a Sheldon model, but as far as the RPA is concerned, you don't really.
Doesn't matter.
It doesn't really matter because it's an excitation on top of that. Yeah, as you can always ask for an excitation on top of a ground state. Whether the ground state is stable or not, that's a separate question.
And then, I think you just said this, but just to make sure I understand. On one side, you have electrons being dynamical things, on the other side, you have protons. The thing is different between them is just their mass.
That's correct.
Then the rest of the parameters are held fixed, like the chemical potential, let's say, the density is held fixed, and just the mass is being varied. Is that the idea?
Well, naturally, we'll have a much higher chemical potential when you calculate it.
I realize the density is right.
Yeah. Yeah.
So the density is being held fixed, and all is being dialed as the mass, and you get either an extremely skinny thing or a more flat.
Exactly.
That's what
So let's continue. So why is that thumb-like structure coming up? You can calculate the imaginary part in hard-dense loop approximation. So that's basically assuming that your energies and momenta are small compared to the chemical potential and the Fermi moment of the particles. And then what you will find is a sharp cutoff at Q0 equal to VF times Q. So that's what you can see on the left-hand part of this picture for electrons. So it's kind of unphysical to assume that when you come from a time-like region from above, where the system is unscreened, that the system will abruptly become very strong in the screens. So in the background here in this plot, you see the density of the imaginary part. So it peaks around that line VF times Q. So what really happens is that if you don't do the hard-dense loop approximation, but you do the full momentum dependence, then the spectrum will set in smoothly but rapidly. And if you have very massive particles, such as protons, then the violation of the hard-dense loop criterion that Kf must be much larger than Q0, and Q is much more strongly violated. So what you can see is when you go to higher momenta, the imaginary part kind of smears out around that value of Vf times Q. It doesn't go to 0 so sharply. And now you can understand why the plasma mode actually obtains this shape. It goes up in energy as long as it's in the unscreened region. Then it reaches this screened region where it loses energy rapidly, and losing energy rapidly in this diagram means it bends downwards and at some point emerges with the gap mode. So that's really the origin of that weird shape.
And omega 0 is the plasma frequency?
Omega 0 is the plasma frequency at Q0 equals 0.
Okay.
So the standard definition of the plasma frequency.
Definition, and MD is the divine mass.
It's the divine mass.
Also the related to the plasma frequency are identical to plasma frequency. Is there any factor between M divine and omega?
There's I mean, there is a constant factor in between them. I don't know by heart now, with probably 1/3 or something. So then we're interested in the photon spectrum. So now we can look at what the spectrum actually looks like. So if you are in a space-like region, you find the Landau damping that we have been discussing so far. So you see R and I are the real parts of pi and the imaginary part of pi. So that gives you this continuum spectrum. So both horizontal axes are now normalized over Vf times Q. That means that for both electrons and protons, the spectrum, the continuous spectrum, goes to 0 at exactly 1. And then I plot the longitudinal modes and the transverse modes. So you can see this dot dash line again here. That's that's really the spectrum of, oops.
So you talk about space-like and time-like regions. Can you define that?
So space-like is the region where, so in space-like, the free momentum Q is larger than the energy Q naught, and in the time-like region, Q naught is larger than Q. So that's really, if you look back at this diagram, basically the undamped region up here, that's all time-like. The damped region down here is all space-like. And this is really the transition that corresponds to this point where VF times Q naught over VF times Q is exactly 1 for electrons, because they're space-like and time-like is basically the same thing. So you have this dot dash mode here. That's the mode that is actually down here below the line VF times Q. You can see that it's strongly damped. And then you leave this, you leave the space-like region, and at some point when you go up in energy, you hit the plasma frequencies. So imagine that you go on a straight line somewhere here and you proceed upwards. You first hit this damped mode in the continuum, then you leave this continuum, you enter the undamped region, and you hit the plasma mode. That is what you can see here for the two species, electrons and protons, where electrons are the purple lines and protons are the blue lines. So that's how to read these diagrams for the longitudinal spectrum and the transverse spectrum. So that was the warm-up of a simple one-component plasma. So now the question is, we would like to generalize this. So let's look at electrons, muons, and protons. And let's start with considering pure electromagnetic interactions at first. So we're just talking about QED. So then the first thing you have to do is you take your polarization functions and you generalize them in, let's say, an internal flavor space that is spanned by electrons, muons, and protons. And then basically you go through with the same thing. You calculate your Dyson equation for the photon propagator and you invert it. And at the end of the day, what it amounts to really is that you have a dressed photon propagator, which now has the trace of all these polarization functions in there instead of just one of them. So then you have chemical potentials of electrons, protons, and muons. They need to be fixed somehow. So what you usually do is you fix them by charge neutrality and beta equilibrium. And I will say more about the beta equilibrium later, so that's already related to the nuclear part. But let's for now just say I fix it by charge neutrality and beta equilibrium. That gives me the values of the chemical potentials. And also, I have to take into account that protons in dense matter, they're actually not bare protons. They're strongly interacting particles, so they will acquire an effective mass. So the whole technology to do an RPA resummation, if the plasma consists of multiple components, is actually very well established. And I'm going to apply it in the following. So what happened to the excitation spectrum now? So you can see that now you can trigger actually separate response of all these particle species. You get a response of protons, that's the blue lines down here. You get a separate response of muons, which is the green one. And you get a separate response of electrons, the purple lines. The thick black line on top of all of this is the transverse mode. So there is no fine structure in the transverse spectrum, but there is a very subtle fine structure in the longitudinal spectrum. So what you can see here is that there are the damped modes for electrons, muons, and protons. So basically, everything that lies in the time-like region now is damped because you have to add up the damping contributions from electrons, muons, and protons. You can also see that the plasmon modes that would exist separately for electrons, muons, and protons have been reduced to sound modes. So now both parts of the FUMP that we saw before, which are lying above and below the lines of VF times Q separately for electrons, muons, and protons. So for protons and muons, both of these lines now go to zero like a sound-like mode. And the reason is that as long as you have much lighter particles in the spectrum that can efficiently screen the heavier ones, the gapped plasmon excitation gets reduced to a sound mode. So that's actually a a fact that's very well known in solid state literature. These modes have been termed Bohm-Stauber sound modes, and you recover them also in this spectrum of dense nuclear matter plasmas. So you see here the strongly damped modes, which are below these lines. You see the damped modes, which are above the line, which have been reduced to sound modes, and you see one overall plasma mode that corresponds to the original electron plasma mode. Okay. So we can again look at this in the context of the imaginary part. So you see that the imaginary part actually peaks around here, so that's the contribution for the protons. But then you can also see some subtle fine structure between the contributions from muons and electrons. So when you put the excitation spectrum on top of that imaginary part density, then you see that actually all of these modes are damped to some extent, except for the real electron plasma mode. But the proton modes are certainly the ones who are the most strongly damped.
What's the color scheme? Is it the density?
It's the magnitude of the imaginary part. So the magnitude of if you're in this region, you only have electrons contributing to the imaginary part. If you're in this region, you have electrons plus muons contributing to the imaginary part. If you're in this region, you have all the free species contributing to the imaginary part.
How much does the value of function change when I go from blue to something that's colorless, like light yellow?
Yeah, the actual number I would have to look that up, but the spectrum is heavily dominated by the protons. That's why the subtle differences between the muons and the electrons are not that much visible. But so let's again look at the spectral functions. So you can see here the spectrum of the modes. The dot dashed lines are the modes. Again, below VF times 2, the dashed lines are the sound-like modes. And then here you can see the actual plasma mode of the electron. And what you can find is that, so the position of the collective excitations kind of follow the shape of the spectrum, which is not surprising. And you can see that it is actually really quite complicated. So the spectrum of the longitudinal modes in the background of this free component plasma becomes strongly modified. The same is also true for the transfer spot, even though the details here are not as much complicated as for the longitudinal piece. So I want to remind you at that point that to my statement that I made in the beginning, that the static part would actually predict that the longitudinal piece is screened by a constant basically, and the transfer piece is not screened at all. So this really underlines how important dynamically screening effects are if you're looking into transport coefficients at the core. I would say they're really an important piece of physics that should be included in the calculation. And here in the bottom left corner, you see a 3D plot of the spectrum, how it evolves along these three lines, BF for protons, BF for muons, and BF for electrons. So I'll get started with including nuclear interactions. So far we've only discussed QD. One question that immediately pops up is, what's the role of the neutrons? So cold and dense neutron stars are certainly extremely neutron rich, up to 95%. And if you look at the coupling to the photon in free space between from neutrons to photons, then it's actually really tiny. It only emerges from that coupling to the magnetic moment of neutrons. So then you could argue, what are the neutrons doing? Are they just observing and just spectating any process? But it turns out that's not entirely true, because neutrons are strongly coupled to protons, and the protons in turn, they can interact electromagnetically with any other particle in the plasma. So you get an interaction that's induced by the polarizability of protons, and that is actually sizable. That can change the picture quite a lot. So what I'm going to do is I'm going to use the resummed polarization tensor for the protons. So imagine that you have a subspace that is in which protons and neutrons live, and you want to resum the many particle effects in this subspace, so that only concerns the protons. So basically you end up again with the same photon propagator, but this time the electrons are still the bare electron loops, the muons are still the bare muon loops, but the proton is this resummed proton function, which knows about the nuclear interactions and the induced coupling to neutrons. And then you can ask again how this picture changed. So when you expand the photon propagator, then you see what actually happens. So to leading order, you find an alpha F, so an E squared correction for the electrons, muons, and protons. But the protons, they're actually not the bare protons. They are really, what they really are is they are resummed particles in the nuclear interaction. So you can expand that last bubble further, and you will see that you get all the interactions that arise from the nuclear potentials. And you can see that the neutron, it factors in at this level, where you really see that proton, neutron, proton loop pops up. So this is really how the nuclear interactions enter in this game. So as I said before, we should treat the nucleons as quasi-particles, and we should obtain their properties from from liquid theory. So there are a lot of energy functionals out on the market. This is the one I choose. The reason why I use this one is because it actually depends not only on the nucleon density, but also on the currents. And if I want to understand the response coming from the response to the longitudinal piece and the transverse piece, I really do need the current interactions in the system. So there's this energy functional which has this work. It depends on these coefficients, Cn, C tau, and Cj, and it can be related in some way to a Skyrm energy functional. I don't want to get into the details of this, so this is very well worked out, and it's all in this paper by Jamel and Hansel. And now I can use this energy functional to extract my nuclear potentials for the spatial part and also for the density piece. And I also extract my effective masses basically by doing functional derivatives of this energy functional. So there are a lot of these parameter sets for Skyrm forces on the market. I've listed the one that I've used here for comparison. So depending on which group you're looking at, some might prefer one parameter set, some might prefer another. That's really a matter of taste, but the one that I use here are ones which are very well established and pass a lot of macroscopic constraints, so they're supposed to be good for Skyrm forces.
So just to make sure I'm following, so in the previous slide, you're basically making the point that the role of neutrons is just through the dressing of the protons. So when you earlier said that the proton mass is not the one we're used to, but the medium proton mass, that's this effect of neutrons. So now you're trying to estimate what is the right value to use for the medium proton mass. Is that what it's going to become?
So the protons have
they're charged here.
The protons have an effective mass anyway, because even if you were just looking at, you don't care about induced interactions, just look at a Fermi liquid and they get an effective mass. Mm-hmm. So they themselves are quasi-particles. What I'm doing here is I resum the RPA. So that's so that gives me the excitation of a different kind of spectrum, right? It's not the quasi-particles per se, which are the quasi-protons and the quasi-neutrons. It's the long-range excitations that I get from resumming the RPA. So there are two levels of quasi-particles in the system. So here's some plots to show what the results are when I extract effective masses, potentials, and number densities from this Skyrm energy functional. So the dot, so in the upper left one, the dot dashed line is the muons. You can see that they enter the game around 0.7 times saturation density. And then the thick black line is the protons. So as soon as the muons set in, the proton spectrum is actually the sum of the muon spectrum and the electron spectrum. Then you have a thick gray line to the left. So anywhere in this region, nuclear matter, homogeneous nuclear matter, is unstable. So it's very well known that when you go to low enough densities, homogeneous matter wants to cluster. That is also known as the spinodal instability. So you can calculate this onset of this instability, and then you should restrict yourself to anything that's to the right side of this line. And then you can see the effective masses of neutrons and protons, the nuclear potentials, and the current interactions. So you can see, actually, depending on which Skirm force you choose, the values might differ quite drastically. So this is to say, if you want robust results, you should probably restrict yourself to not much beyond 1 times saturation density. So you can see how big this band is when you go to up to 3 times. And another important point is that the whole energy functional is actually defined non-relativistically, that I showed you before. And I said in the beginning, I'm doing a fully relativistic study. So that means you have to be careful when you match all these coefficients. For instance, chemical potentials are differently defined for non-relativistic and relativistic physics. So that's just one subtlety that you have to be aware of. Okay. So the easiest thing you can do now is you can ask for the screening mass and the static limit again. So now I'm just looking at the strongly interacting sector. So I just want to know what is the contribution to the proton screening coming from protons and neutrons which are interacting strongly. So if I take the static limit of the resound polarization tensor, it's giving me this expression. It's not surprising that in the static limit you should obtain that screening actually from mere thermodynamics. So what it really is, it's calculating d mu over dn, assuming that mu is has an implicit dependence on mu neutron. So if I calculate d mu proton depending on d mu neutron over dn proton, then this is exactly what I get. And then I can plot this for all the different kinds of Skirm parameterizations. And what I find is that independent of which Skirm force you choose, naturally there's a very strong impact of the induced interactions on the screening. And so these 2 important pieces of physics, the dynamic screening effects that come from QED that I discussed in the first part, plus the induced interactions coming from nuclear physics, should now be combined to give a more realistic shape of the photon propagator. So now when I do that, I can again look at the spectrum. So I want to remind you about that graph that I showed before. Oops, this has very bad resolution here. Where you had this separate responses of protons, electrons, and muons. And now I can add the strong interactions into this game and ask the question, what happens, what changes? So because the protons, so the first plot I'm showing you is at roughly 0.8 saturation density. So let's go back once again and see. So if I'm at 0.8 saturation density, then it's better visible here. And I see that my screening is actually strongly enlarged compared to what it would be without induced interactions. When I go to higher values, I can see that my screening gets reduced. So in this case of 0.8 times saturation density, my screening is strongly enlarged. So the protons are subject to very strong screening coming from strong interactions. Whereas the other particles, muons and electrons, are not. So that means that the muon spectrum becomes more and more relevant over the proton spectrum. And this is something that you can see in the excitation spectrum, because here you see that the protons, they don't have a completely independent response anymore for sufficiently low densities. You see that you only have the response of the muons. So now I can turn the game around and I ask for the case where I'm actually at higher densities. So now the proton screening is actually strongly reduced. So you can see the protons themselves, they have a perfectly well-defined excitation spectrum, but their spectral function dominates over the muons now. So the muons are the ones who, at lower momenta, don't have a well-defined spectrum on their own anymore, and they merge with the electron mode. And then here on the right-hand side, you can see the spectral functions. So at 0.85 times saturation density, you see that indeed, the pure QED spectral function of the proton is much larger than the one where you have strong interactions. Oops. And in the other case, at 0.6 times saturation density, it's exactly the opposite. The effect is completely reversed. So QED plus strong interactions gives you a higher peak in the spectrum for the protons compared to just QED, and that's because screening of the protons is reduced at that point. So I'm actually said most of what I wanted to say. So as a short outlook, so where do we want to go with all of this? So as I said in the beginning, one of the strongest motivations is to refine existing calculations of transport coefficients using a much better description of longitudinal and transverse photons in the dense plasma. That's what we're doing right now. We're also including effects from nuclear neutron Bremsstrahlung. They might not do a lot of modification in the low momentum spectrum, but when you go to higher energies and momenta, these corrections become relevant. And then, so one of the weak spots of this analysis is certainly the way how nuclear interactions are implemented. Is simply extracted from Landau-Fermi liquid theory. So it would be interesting to see if there is something one can do better, maybe based on relativistic mean field models or other models, whatever is suitable for this region. Then it would also be interesting to study the impact of pairing on this project. And then finally, once you have a very accurate description of the photon spectrum in dense nuclear matter, you could also ask questions which are not directly related to neutron star physics. You could ask, for instance, what's the response of having a dark matter particle that traverses through dense nuclear matter? So these are some things that I would like to look into in the future. So thank you very much.
Yeah, thank you very much. If you have any questions, please indicate so in the chat. Otherwise, are there any questions here? I wanted to ask you, the results you showed in the last plot, they were for one square interaction?
Yes.
So how does it change for different interactions? And the interactions you chose, they are all fulfilling this constraints by neutron, right? What if you choose a very extreme parameterization? Or something that's
right. So I think the answer to your question is actually in this plot, because all the way how nuclear interactions factor in is coming from this resummation of the proton bubble. So basically, these differences that you see here are the ones that are getting translated into the QED calculations, because the nuclear interactions appear nested in this QED calculation. So whatever happens here is also going to affect the spectrum of the photon.
Curves corresponds to a different model that we use.
Yes, and then so there is so as you said, there is this review paper by Dutra where she compares all the existing square parameterizations and rules out some of them based on microscopic constraints. So the dashed line in there, that's the SLY4. That's actually one that was ruled out by Dutra. The reason why I have it in my comparison is because the energy function of Chamel was based on this one, and I wanted to have this in the calculation to have some means to compare whether my results are correct or not. But you can see as soon as you put one in that actually faces microscopic constraints, it really enlarges the.
So the one on the right, of course, is just everything, not just the microscopic constraints.
Yes.
But the general features stay the same. I mean, you see it.
Yes.
Okay. Herman had a question. I don't know if he has a microphone to read it himself. Otherwise, I can read it. Or yeah, he asks. Does the density where major effects are found correspond to the transition from the crust to core of the neutron star? Emma, do you have a microphone?
So what exactly do you mean when you say corresponds to the transition from crust to core in the neutrons?
I don't know. Let me know if you can hear me.
I can hear you, but barely.
I'll try to speak up. So you said it was 0.85 saturation density where you had the
yes.
major difference. Yeah, the only reason I'm interested is because in the previous paper we found that the region between the inner crust and the core is where induced interactions have bigger effects for transport properties. So this seems to agree with that statement, that you have this change. So that's the only reason why I'm interested. It might actually be even stronger, the effect from induced interactions with this calculation on the transport properties. Like,
okay, so I didn't get the first part. So you say it might even be stronger. Why?
Because we just did a very simple calculation in the first paper we did without doing the full RPA like you're doing now.
Oh, I see.
So, so that's why I'm wondering what the effect of this would be on the transport properties later on. So once you take all of these and you try to see what happens to the shear viscosity, for instance.
Yeah, exactly. So that's that's the whole point of the project, right? So as soon as we're plugging this in right now into the transport codes, and we see what happens. So hopefully,
it sounds promising because of the range. Yeah.
Yeah.
Okay, are there additional questions? If not, let's thank Stephan again.